Hello student, this is lecture number 4 of chapter number 7 and the title is Energy and Magnetic Field. How the energy stored in a magnetic field we are interested to discuss here. The work done on a unit charge against the back EMF and one trip around the circuit. The negative sign shows that the fact that the work is done by you against EMF. And here the energy is stored in the magnetic field and it is recoverable. As by definition, the work done by a unit charge in one trip, and this is equal to minus EMF, means the work done mathematically, I want to write down the work done per unit charge dq, this is equal to minus EMF, the work done per unit charge, which is equal to minus EMF. And here if I extend this equation and if I write down dw divided by dq divided by dt and dt, this dt, then it will cancel out and we have the same result. Then dw divided by dt, which is equal to minus and dq divided by dt, and dq divided by dt is nothing but this is the current, and further dw divided by dt minus ei, because dq divided by dt is known as the current. And we have this equation. It means that this dw divided by dt, which is equal to minus ei, and what is EMF? This EMF, if you have only one loop, one circuit, then this must be di divided by dt minus L di divided by dt. This is the self-inductance, and putting the value of EMF here, then minus minus will cancel each other, and I can write this L d L I di divided by dt. Look this equation, and if this dt, if I cancel out this dt with this dt, then we may have dw, which is equal to IL di. If we take the integration here, this integration will be because di, so I can take like this. This is the integration, and this is from 0 to w, and this is from 0 to I. So by integrating this will come, we have w, which is equal to L I square divided by 2. It means that this w, which is equal to 1/2 Li square, this is the w. So this w that I have calculated here, this is equation A. Let's consider this is equation A. Another way to write w as, another way to write the w as because we know about the flux. This is the surface B dot dA, and we know about B, which is the curl of vector potential, del cross A dot dA, and using Stokes theorem, then this equation phi, which is equal to, by using a Stokes theorem, then this surface will convert to the line integral, and A dot dl, it will come A dot dl. And let's say this is equation number first. From self inductance, we also know from self inductance. From self inductance, we know the flux is equal to Li, and this is equation number 2. This is flux. We can compare this equation 1 and equation 2, and what we can get, let's see. Oh, sorry. This is equation number 1, phi, which is equal to A dot dl. This is equation number 1. So comparing equation 1 and 2, comparing equation 1 and equation 2, what we can get, phi, it means that Li, which is equal to integral of A dot dl, and so if I find out the value of L, it will have simple mathematical expression. L is equal to 1 over I integral A dot dl. Now putting this value of L in equation 1, the work done that we have already calculated. So putting this L in equation A, if we put the value of this in this equation, then W must be equal to 1 over 2, and this is 1 over I integral A dot dl into I. It means that I think this is I square. This may be I square. And this I will cancel with this square, and we have the value 1 over 2 I integral of A dot dl. If we shift the I, we can also write down, shift the vector from dl to I, then this equation must be written like this: 1 over 2 integral A dot I and dl. Here shift the vector from dl to I. So this is the equation that we can write down. Now this equation that last we have calculated, this equation, this has some advantages. This equation, the advantage of this equation is one can use this equation for surface current density as well as for volume current density. It means that we have calculated this equation and this has some advantages. We can use this equation as a surface current density as well as for a volume current density. For example, if I write down this equation for a volume current density, then I must be replaced by J, and then we may have the equation 1 over 2 and V A dot J into DL. And let's label this equation as B. We found two equations A and B from the previous calculation. Now to find a third equation in terms of B. Now to find a third equation in form of B, magnetic field. Already we have calculated two equations, equation A and equation B. Now we are interested to find out the third equation in term of B by considering del cross B, which is equal to mu naught J. This is the Ampere's law, differential form of the Ampere's law. So from this equation, if I find out J, then 1 over mu naught del cross B will take this form. And putting this value of J in equation B, putting the value of J in equation B. Now here there are some mathematical steps because I have to find out this W, then we must have the solution of A dot del cross B, and this we have to find out. We will use the identity. Let the identity is if, for example, if I write down the identity and this identity is del A cross B, which is equal to B dot del cross A minus A dot del cross B. And we are interested to find out this because we have A dot del cross B here, so we need to find out the value of this. Then I will take this from this side, A dot del cross B, which is equal to B, this one, and this has del cross A, which is equal to B, and this must be negative del dot A cross B. We have this value that we have calculated from this identity. We now put the value of this here in this equation, and let's see what will be the solution. B dot B, this I can take this B square, so this is actually B square, B dot B, the dot product of magnetic field. I can label this as an equation C. So putting the value of this in equation C. Please write down, putting the value of A dot del cross B in equation C. What we can get if I put the value, and after some mathematical steps I can find out integral b square d tau minus integral del dot A cross B and d tau. So this is the final equation. This relate to the volume, so we can take this as a volume, and by using here a divergence theorem, if we use a divergence theorem here, then what we can get from this left side using divergence theorem. Using a divergence theorem, this part, the volume part, must be converted to the surface, and one can get the surface and A cross B dA. So the final equation, we have a final equation 1 over 2 mu naught volume b square d tau minus integral, we have converted it to a surface integral, A cross B and dA. And this is the another equation. Already we have find out two equation, this one, and this is the another form, and this is very important because we can take the volume and the surface and as well. And now this equation, let's see this equation D, how we can define this equation D. This equation D tells us that the work done is due to volume, this is the volume, and surface integral. If we increase the volume, then the contribution of volume integral increases, whereas the surface integral decreases. So how to understand this physically? This is the point, that how we can understand this. If we increase the volume, the contribution of volume increases, and whereas the surface integral decreases. So let's see, I want to disclose this point. Let's consider we have a surface current distribution. There's some current distribution in this surface area, and this surface area, if we if we remain this surface area, this is constant, and if we increase the volume, the current distribution remains constant, then the contribution of volume increases as compared to the contribution of surface. So I will write down this in detail because this is an important point. It should be noted. It should be noted that the total energy of the system remains constant. This is important. Remains constant. The total energy of the any system, it must remain constant. If we increase the volume, this is important point, but not the current distribution. The current distribution is constant and we increase the volume of this system, then the volume integral increases, but the surface integral becomes negligible. Okay, I will write down here. If if we increase further the volume integral, then the surface integral goes to 0 as compared to volume integral. If we increase the volume, this is the surface where the current is distributed. Then if we increase the volume and the current distribution, which is very small as compared to the volume distribution, so it means that the volume integral is very large as compared to the surface integral. So it is negligible as compared to the volume integral. So we can say that for the whole space only the volume contribution will occur. Finally, if I write down this point, that the surface integral will vanish, and for all space the contribution will be only in volume and the surface will be neglected. So this is the final result of the energy stored in a magnetic field. Here, the energy stored in per unit volume B square divided by 2 mu naught. This is B square divided by 2 m naught, or we can also write down A dot J in the previous equation. This is actually store and magnetic field, the energy store in magnetic field. From this, one can think that the energy stored in the current distribution, per unit volume. Previously in chapter 5, we have calculated the energy stored in electric field like this 1 over 2 V rho d tau, and this is equal to epsilon naught divided by 2 E square d tau. This is actually the energy stored in magnetic electric field. And now in a magnetic field, we derived 1 over 2 A dot J d tau, which is finally equal to 2 mu naught B square d tau. Now let's see the comparison between the energy stored in electric field and the energy stored in a magnetic field. The comparison is very clear. Here, this is a scalar potential. V is a scalar potential, and rho as charge per unit volume. And here, epsilon naught, we have electric field, so we will have epsilon naught, and this is the electric field. And the energy stored in a magnetic field we have derived. This is the vector potential, and this is the magnetic field. So there is some similarity, and we have also the mu naught, which comes in the magnetic field. So there is some similarity between the energy stored in the electric field and the energy stored in the magnetic field. Both have the same equation, but little bit different.